stability and of the material is also the one of the criteria which has to be checked. And for the strategy for the energy engineering heterogeneous catalysis is the catalyst should have to be heterogeneous semiconductor. It should have to be enhanced visible light induced so that it can be used splitted using the visible light, and it should be safe and cheap so that it can be easily prepared, and the stability should be there, and efficiency should have to be high in a sense like if we use water, it should generate more hydrogen and oxygen in the reaction. So for this, these are the one periodic table. So usually the D0 group semiconductor material is one of the best suitable materials or the catalyst used, and the earth abundant materials like chromium, zirconium, iron, or nickel, it can be used as a co-catalyst, as well as the transition metals can be used, and even we can use the plasmonic metals like silver and gold nanoparticles for the co-catalyst to enhance the reaction. And normally this is the band gap semiconductor. So before doing the experiments, we should have to know the band gap structure. So we should know the conduction band and valence band position. So if you know the conduction band and valence band position, then only you can choose whether this material is suitable for the photocatalytic hydrogen evolution. So normally the more the negative potential of the conduction band and a stronger reduction activity happens, and the more the positive potential of the valence band, the stronger the oxidation reactions happens. So you should have to choose the suitable band gap material. And strategies to enhance the photocatalytic activity is like band gap engineering, doping, multi-component, and these are the one of the other criteria. So this is the one of the biggest research activities which is going on in the heterogeneous photocatalytic hydrogen evolution. So I'm just dealing only Z scheme and S schemes strategies for the heterogeneous junctions in this particular talk. So this is the one of the criteria. The light should have to have you induce a localized static state such as the donor level. So if you use the donor level, it or the acceptance level in between the semiconductor process, so it can generate a narrow band gap so that the band gap can thus enhance the photocatalytic activity. And as well as the PN junctions, so it is one of the suitable junctions when you prepare the two heterogeneous catalyst for the photocatalytic electron hole separation for the hydrogen evolution. And solid state reaction. Solid state reaction is nothing but like this is a zinc sulfide, and this is a cadmium sulfide. So you prepare something like a mixed zinc cadmium sulfide. So if you prepare combined with both with the 0.5 cadmium sulfide production, so as you can see here, so if the pure zinc sulfide generates a very less hydrogen gas using the photocatalytic reaction, and the cadmium sulfide is since it is a visible light induced catalyst, it can generate a little more higher photocatalytic hydrogen. But if you combine these two together, zinc sulfide and cadmium sulfide, and make a semiconductor solid state reactions, it can enhance or boost the hydrogen evolution from the almost like 1 or 2 millimole, it has jumped almost like to the 7.5 millimole hydrogen evolution. So this is one of the strategies so we usually induce. And apart from that, the micro or nano engineering, the micro and nano engineering in a sense, like if you use a solid sphere, or if you prepare just a solid sphere catalyst, once the light is ignited, illuminated, it gets reflected very easily. So if you prepare the Olchin like halo spheres, so once the light is ignited, it gets multiple reflection, and then since it gets multiple reflection, it has a more opportunity for the electron hole generation, and it enhances the photocatalytic activity, as well as the same with the halo spheres. So the better the So we have to think about the nano engineering aspects, how to generate the architecture, how to prepare the nanomaterials. So, and apart from that, the types of interface like a homo junction or like a NN junction or heterojunction or the co-catalyst with the semiconductors and heterojunction carbon materials are one of the criteria which we have to generate or check. So this is one of the interface engineering junctions which most of the researchers adopt. So it is like a single phase junction or rutile. This is a rutile with the anatase heterojunction, the first one. And this is the NN heterojunction. NN heterojunction in the sense both are catalyst or the semiconductor have a N-type conductors. And this is the PN heterojunction. Then the PN heterojunction is the more suitable for the photocatalytic hydrogen evolution as well as the other application. And since you can see here, if it is an NN type, so the mobility of charge carriers like the holes from the semiconductor one, it can once the charge are ignited, it can easily jump from the semiconductor 1 to the semiconductor 2, and then it can easily reduce, and as well as the holes from the semiconductor valence band from the semiconductor 1 can mobilize to the semiconductor 1, and then it can oxidize. So this is the oxidation and reduction process which we use for the developing the type 1 semiconductor and type 2 semiconductor and type 3 semiconductors. There are three type of usually semiconductors which we use, and interface is also one of the criteria. It's like if you have prepared quantum dots or 0D materials, and if you use 2D materials like a graphene or carbon nitride or some other materials, so you can generate the point contact, or you can just generate a line contact using the 1D and a 2D material, or you can generate a phase contact using the 2D materials over the 2D materials. This is the strategy used for the heterojunction, and this is the Z-schemes method which we use. So once in this one, you can see the charge generated from the semiconductor tube. It is moves to the semiconductor, electrons moves to the conduction valence band of the semiconductor 1, and then it further ignites to the valence band, conduction band, and then it reductions happens. So this is zinc oxide and the cadmium sulfide which are used. And apart from that, we also use the silver or gold nanoparticles or plasmon semiconductor materials. So if you use the plasmon semiconductor materials, it also generates the internal electric generation, and this is one of the strategies. So in between the semiconductor 1 and semiconductor 2, we can fuse the electron radiation mediator like a platinum or silver or gold nanoparticles, or even we can use some copper or any other metals. So this is the NN type of semiconductors. So I just skipped this one. So this is the semiconductor motors. And apart from that, we also use the co-catalyst like the co-catalyst. Either if you use a co-catalyst like a silver or gold or platinum nanoparticles, so it is like a volcanic type of activity. So if you co-dope or dope higher the co-catalyst, the photocatalytic activity or the catalytic activity decreases. So you should have to find the optimized level or the optimized loading of the co-catalyst, which is which can generate the highest activity, photocatalytic activity. Photocatalytic activity in a sense like hydrogen evolution. So this is the platinum which usually we use. So platinum also acts as an electron sink, and it also provides effective proton reduction sites. And if you use a platinum, you can generate or prepare platinum nanoparticles of different size, like octahedron or cubical or any other shape. So depending on the shape of the co-catalyst, the photocatalytic activity increases. You can see here when the platinum nanoparticles are co-deposited or deposited or loaded over the carbon nitride material. So the cubic phased one shows the lower one, whereas the sphere platinum nanoparticles with a sphere shape shows the highest activity compared to the cubical as well as octahedron nanoparticles. So this is one of the criteria for the preparation of the materials. And apart from the noble metals, we can use the copper, nickel, cobalt, or molybdenum or tungsten materials as a catalyst. So this is the one of the graphene-based material which is used for the photocatalytic hydrogen evolution in our group. So we have prepared graphene nanoparticle, 2D nanoparticles, and over which the cadmium sulfide was loaded. So if you see the material, so you can see the hydrogen evolution during the, this is an incentive reaction in the sacrificial agent. So you can see the hydrogen bubbles forming inside the water, and this hydrogen bubbles, due to the density it forms on over the surface, and this can be extracted and it can be used. This is the reactor actually. So this is the quast reactor and this is the catalyst, and the light is ignited from the top. So you can see the light is ignited. It's a 350 watts xenon lamp light. So depending on the doping of the graphene concentration, so you can see the graphene with 1%, just by adding 1% of graphene in the cadmium sulfide. So you can see the photocatalytic activity has drastically increased. So this is one of my paper which has been published in Applied Catalyst B. So here you can see the zinc oxide and zinc sulfide combined, which shows like a bouquet-like structure. Over this bouquet, there is a what you call the copper hydroxide has been deposited as a cluster, as a small clusters, small clusters. So these small clusters acts as a co-catalyst for the hydrogen evolution. So you can see the zinc oxide, since it is visible, UV induced, you cannot find any hydrogen gas. So in the zinc sulfide, it generates a very small amount of gas, hydrogen gas. But if you combine these two together, so you can see this one, it generates almost like a 29 if you combine these two. But if you add a copper hydroxide as a co-catalyst over the surface of this catalyst, so it enhances the photocatalytic hydrogen evolution from almost like 29 micromole to 1300 micromole. This is one of the process we usually develop. And apart from the other co-catalyst, we can use iron sulfide, nickel sulfide, or many other sulfides. So out of this, most of the researchers usually use molybdenum sulfide. Even we have used molybdenum sulfide in this one. So this is one of my experiment where I used a solid solution zinc cadmium sulfide with graphene oxide. So you can see this is a pure zinc cadmium sulfide, and over this a thin layer, a small sheet, a transparent, very thin transparent graphene composite is been draped over the surface. So you can see the graphene here in the TEM. So once we use this one, in between that one, over the surface of that, I just deposited a few sheets or thin sheets of molybdenum sulfide. So you can see here pure cadmium sulfide has just 5.7 micromole of hydrogen gas. But if you had graphene of like 1%, it generates a 20.1 micromole of gas, hydrogen gas. So the same material, if you see here, this is the same one. So if you co-deposit a molybdenum sulfide on it, so depending, if you vary the concentration of molybdenum sulfide at optimum percent from 20 or from the 5.7 pure one with the graphene oxide with 20, it increases to 39.7. So this is one of the process which usually developed. and this is also one of the material used for molybdenum sulfide. So I just skip it. And this is cadmium sulfide and zinc sulfide core shell structure. Cadmium sulfide is a 2D or a rod-like structure. Over this rod, a thin layer, a transparent layer of zinc sulfide is coated. So it's a coated. Over this coated zinc sulfide, a few layers of molybdenum sulfide is being deposited by the deposition method. So I use a hydrothermal and other deposition method. So you can see here in this hydrogen evolution experiment results. So the pure sample shows almost like a 5089 micromole of gas. So once you deposit like 7% of co-catalyst of molybdenum sulfide as co-catalyst 2 layers, it increases from 5,000 to 13,000. So this is how we usually increase. And apart from that, if you use platinum, if you don't use the molybdenum sulfide, if you use platinum, it shows 5,200. Or if you use the palladium sulfide, it shows 10,000. So if you exclude a platinum and palladium because it's expensive, if you use a molybdenum sulfide instead of this highly expensive catalyst, even that also can produce a very high hydrogen evolution. So that is how we can cut down the cost of the catalyst price. And so you can also see here, this is the process actually. This is cadmium sulfide, pure cadmium sulfide, and this is pure zinc sulfide. So if you combine these two together, then it produces this 1184. So if you combine this with the proper concentration, then it increases here. So from here, it jumps. So this is the schematic illustration how the electron holes mobilize, and from zinc sulfide to the cadmium sulfide. And then from cadmium sulfide, it jumps to the electron, jumps to the molybdenum sulfide solution, and where it splits water to hydrogen, as well as in the conduction band, valence band of zinc sulfide, the water is split into oxygen. So this is one of the other experimental method which we use for the hydrogen production using the tungsten oxide on the carbon nitride. So, and roadmap, if you see the roadmap of the Z schemes and the S schemes photocatalysis, as I showed in the earlier previous slides, in 1972, Honda and Fujishima, they prepared the first photocatalytic activity. From there, it has improved a lot. And this in 2013, in my previous group in Wuhan, they produced the hydrogen direct Z schemes process. And in 2019, in her group, we produced, we have in our group were the one who introduced Z schemes and S schemes to the system. And from there, a lot of research has happened. From 2019, when our group introduced the Z scheme process, so you can see a lot of publications are coming out each year on this process. So it shows that the process is very quite effective, and as well as this is the very induced one. So since a lack of time, I just skip a lot of process. So this is types of S schemes which we can produce, either NN type heterojunctions or two semiconductors, and P or P heterojunctions, or PN heterojunctions, or NP heterojunctions. So you can have any type of heterojunctions, and only the thing aspects is like we should know the band gap or the conduction band position or valence band position of the semiconductor 1 and semiconductor 2 to choose which type of heterojunction it is generating, and this heterojunction, whether it is suitable for the S schemes heterojunction or not, we can choose on that one. So this is one of the exact things. This is not her research group work. I just wanted to share this research, two experiments, to show what is how the future is going on. So this is actually the solar-driven photocatalytic hydrogen evolution using the cadmium sulfide and cobalt. Cadmium sulfide and cobalt oxyhydroxide photocatalyst, which has been coated on the surface of the lignocellulose or wood. This is actually a wood, lignocellulose wood. So over this cellulose wood, the catalyst is generated, and you can see a small quantum size nanoparticles has been generated, and it has been deposited on the substrate of the cellulose or wood cellulose. So since it is on the wood surface, you can see the hydrogen evolution, and we can use the biomass also to generate the hydrogen gas. So through this process, even the wood branches or the biomass can be used for the hydrogen evolution, and it also increases, or it acts as a catalyst to enhance or boost the hydrogen evolution. So you can see the right and the left one. So in the left one, which is generating the lignocellulose, the right one is the one which has a lignocellulose, and the other one right. So you can skip this. So you can see with the respect of time, like usually we induce light for 30 minutes or 1 hour. So if you induce a light for 30 minutes or 1 hour, so you can see the hydrogen gas bubbling out from the water or the sacrificial agent. So it is continuous, and you can see the gas generates with respect of time. This is a time process. So this is 1 hour. You can see almost like 100 micromole or millimole of hydrogen gas has been generated. With respect of time, like in the 6 hours, without the cellulose and with cellulose, you can see without cellulose or without a wood, the hydrogen generation is very less or comparatively very nothing. So with cellulose with as a catalyst or the substrate, so the hydrogen evolution is too high with compared to the light. So this was published in Nature Energy Material publication, and this is another experimental work which I want to share on the plastic waste. So not only the wood, we can also generate on the polymer or the plastic or PVC or PVT or PLA polymer. So we can use this as a substrate. Over this substrate, we can coat or deposit the cadmium sulfide or cadmium oxide catalyst. So, and then if you ignite with the solar light or the xenon lamp or the UV light or any other lights, so it can also generate the hydrogen gas over the cadmium sulfide and cadmium oxide quantum dots. So this is the SEM image of the scanned electron image of the PVC pipe or PVC PET bottle, PET bottle, and over this PET bottle there is a cadmium sulfide and cadmium sulfide quantum dots, a small quantum dots deposited over it, and this is the hydrogen evolution, long-term photocatalytic hydrogen evolution. So you can see with respect of days. So this is, it can generate it till the 6 days. So over the surface. So this is the one of the. So with this I conclude. I just want to share that since there is a huge conflict, war conflict and others aspects, so we have depended on a lot of hydrogen energy. So we have to reduce the hydrogen or LPG gas usage, and rely on the renewable resources from the non-renewable resources. So this is the one of the aspects. So now already the hydrogen gas, fuel cells generated cars are already in use. So this can be used for other application as well as not only for the uh, vehicles or automobiles. We can use it for other applications also. So this is how we are trying to reuse or convert it into or reduce the pollution. So with this, I would like to thank you for listening my lecture. So and I
Thank you,
would
sir.
like to conclude this talk. Thank you. If you have any questions or any concerns, you can raise.
Thank you so much, sir, for this insightful presentation. So your talk clearly highlighted how intervention systems enhance
Yes.
solar hydrogen production, addressing both efficiency and the scalability for clean energy solutions. Thank you so much, sir, for the beautiful presentation and for the beautiful ideas. Thank you
Thank you,
so
sir.
much, sir.
Thank you.
Thank you. Thank you.
Okay.
Thank you, sir.
Thank you. I will exit from the group.
Yes, sir.
Okay. Thank you. Thanks you.
Okay, thank
Thanks
you.
once again. Yeah.
Thank you.